In this video, I shall look at one possible approach to defining ordered hash functions when the data is already known. It is basically statistical ordered hashing. So here I basically make use of the mean and the mean distribution in order to define as reasonable. I just take a simple small example, but you can see that it is reasonably effective, much better than just taking the quotient or the leading part of it so as to get hash to the particular table. Here the data is assumed that the data I take here, the thing is we have a set of keys here, ki, that is basically k0, k1 and so on up to k n minus 1. I'll just assume that this set of keys are in order, that is k0 less than k1 less than, but they are randomly chosen from, we have to define a hash function from M to S. It's some randomly chosen of a particular maximum length of bits, in bits or in digits. Now what we do is let the differences be di be nothing but ki plus 1 minus ki. Okay, since they are in order here, we have a set of differences di. So now the objective here is, we have this difference, so we should just calculate first the mean of the differences. K0 will be the least one. Okay, I am assuming these keys are all in order. Okay, so we take the summation of all di divided by n. This should give you the mean, which is k bar. Okay, now having taken this mean, one possible simple hash function would be to define, since the data are all in order, some way is to define k0 plus k bar, hash value to be determined as k bar into v less than or equal to ki. So in general, vi, hash value vi will be vi less than or equal to ki minus k0 by k bar. Okay, so last value, least value is what we are interested in. So this is one possibility. The next, then we have taken di there, then we can take let xi is equal to, we can take the mean distribution, we can make some slight improvement on it as follows. We can take the mean, let xi equal to absolute value of k bar minus di, then the mean distribution of the differences between them would be md is equal to summation xi by n minus 1. Okay, there also the same must be there. When taking the mean, it will be summation di by n minus 1. Okay. So we can calculate the mean. So, and then again the hash can be modified or improved as follows. Vi dash is equal to Vi plus R. Now for each of these key ki, we are calculating Vi as Ki minus K naught by K bar. Let R is equal to Ki minus K naught mod K bar. So if R is greater than or equal to the mean distribution, then we will be using, depending on the size you take. Here what I have taken is I have divided the 10 values into groups of the values that I will be taking. If it is greater than or equal to the mean deviation, then we further distribute it within those values, make improvements to it. If it is less than V equal to mean distribution, then it is, if you divide the table into two parts, for all those values, say for which are greater than or equal to mean distribution, go on the other part, upper part, one, the other less than equal to mean distribution. If R is equal to 0, if R less, right, 0 or 1, depending on whether the value is, that is, then, right, this Vi plus R. R plus Vi plus 0 or 1. If Ki not K, then this value should be 1, sorry, if it is greater than or equal. It is 0 if it is less than or equal to mean distribution. That is basically I have divided the table of 10. In this case I will be taking an example of simply 10 values, some random 10 values that I have taken. I chose to divide it in the 10 values into initial hashing. I will take only 10 as the table size. For the second hashing, where I make use of the mean distribution as well, I divide the table as being composed as 5 into 2. Initially for V it will take, so that those, and use this method and see how the distribution affects the so these are the set of values. This is the basic table that I obtained. First one is, you have here the value, $86, $157, $657, 1314, 1496, 1496, 1879, 3225, 3225, 2. Six, 7, 1, 4. Eight, 3, 7, 4. This is the set of values that I took. Now I calculate, these are all Ki. Now I calculate Di. Differences come out to be as follows. This will be in between, you can take the 71, 500, 650, 657, 182, 385, 1346, 2077, 1412, 1660, 840, 421, 264. Now similarly, I have here xi equal to absolute value of k bar minus di, which gives me 840, 421, 264, 739, 536, 425, 1156, 491. So these are the 10 values that I've taken here. And 739 again. So basically here we have here the set of keys. So difference between this and this, this and this, this and this and this and this difference is this. Okay. Now what happens here is K bar will be summation di by n minus 1 is equal to the summation of all of this will come up to 8290. There are 10 values. So divided by 9 is equal to 921 and 1 by 9. So it will come out to 921. Okay. So this is K bar. Then we have Xi equal to, so you have this table here, you can note it down, this is 536. You can take any set of random keys like this and try doing it. You can take, what happens is if there is more collisions, again you can split it into another table, or ideally S will be slightly large, not too small, say at least 16-bit value means 2 plus 16 or 24. The size of the data set proportionate or just equal to the size of the data set itself. Then what you can do is divide S into smaller parts, that is divide the set of keys itself into smaller groups so that your averages come out to be more accurate and your distribution also helps, so that when the data set is divided into smaller data sets rather than, and then you can perform the same recursor also on top of those values. So that way you should get even a much better performance. So basically this turns out to be the mean of the differences between the key values taken in ascending order. And these turn out to be Xi the values, differences from the mean, absolute differences from the mean. Okay. And the mean deviation MD will turn out to be summation Xi by n minus 1, which is the summation of all of this, will turn out to be 5603 by 9, which is equal to 622 and 5 by 9. We shall only consider 622. Okay? Or if you want to, you can make it 623. Here again we shall consider only 921. Now using this mean and this mean deviation, we'll try to find out what the hash values actually turn out to be. Okay? For the first case, I should take only a table size of 10 only. For the first case, if you have the values Vi turn out to be 0, 0, 0, 1, 1, 1, 3, 4, 6, and 8 for the above. Okay. So see, it is order preserving, and the number of values here is 1, 2, 3, 4, 5, 6 values have been used. Out of 10 locations, 6 locations have been used. Okay, the rest are collisions. Now if I use Vi dash, another instead of Vi, I also use another one which is Vi dash. which is a new one, this one does not incorporate the mean distribution. Okay, this is the values for Vi dash. It will turn out to be 0, 0, 0 plus 1 equal to 1. 2 plus 0 equal to 2, or again 2 plus 0 equal to 2. 2 plus 1 is equal to 3. Four plus 0 is equal to equal to 4. 5 plus 0 is equal to 5. 7 plus 0 equal to 7, and 8 plus 1 equal to 9. For Vi, I take the table size to be equal to 10 only. So directly 10. So for you have Vi is equal to Ki minus K naught by K bar. Vi dash on the other hand is equal to the actual way I took it for this one, the second case, when I divide the table into 5 into 2 as 5 into 2, okay, as K bar, okay. Okay, as 5 into 2. Let R is equal to here Ki minus K naught mod K bar. K bar is the mean of the differences. Okay, so Vi dash will be equal to it should be ceiling of Vi by 2 into 2 plus Z or 1. Okay, 0 if R less than the mean distribution MD, which is 622, right? K bar here is 921, and MD that we calculated was 622, and it is 1 if R is greater than or equal to the mean distribution. I have divided it into 2 only, but you can further again do recursive, no? There, instead of distribution, you can either take mean only again, or mean deviation itself you can use instead of this. Instead of mean deviation, you can also use standard deviation. For standard deviation, square root of Ki minus K naught by K bar, Ki minus K naught whole square, whole divided by n minus 1 should give you your standard deviation. So you can use that, one of these deviations. So this may not always ensure perfect hashing, but it should give you a decent hash for most distributions of data. Where too many collisions occur, you can divide both the data set as well as the table, size of the table, into parts proportionate to that. So if the collisions are slightly small, then here they pretty much match to the same thing. So you can use this kind of statistical approach methods to define perfect, more or less perfect, near perfect ordered hash function. As far as I'm concerned, this is reasonably perfect. It performs at least as much better than, as good as, or if not better than your mod hash function, where the lower order bits, the variation there, even that offers most cases only 50%. This offers close to that itself. And this here does better. 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 values. That the collision 6 out of 10 and 8 out of 10. So clearly by using the distribution facts, also here for this one simple example I have considered, it turns out that the collisions are also fairly significantly better. The distribution is a lot better. So this way you can use these statistical parameters, basically mean and distribution, least value, largest value within that interval, to try and define these statistical methods can be used to define reasonably good hash functions. One way to make improvements of this is, there are other ways of making improvements you can think of. One part is, for instance, if you take, or one is, you can use standard deviation will be equal to k bar some square root of k bar minus ki the whole square. Sorry. Summation k bar minus ki the whole square whole divided by n. In this case, n minus 1. So this will be your standard. Instead of mean deviation, you can use the standard deviation. This is for that set of cases. Another possibility is maybe if you divide the key itself into k is equal to ki itself consisting of k naught square plus k1. Then, because it is taken square, this will skew the distribution towards higher values. You take the power, key is fairly large, it will skew the distribution. So you will, one part of the table and the difference combined with the other part of the table, you can afford to get better distribution. This will skew it if you keep taking powers and keep expressing ki as, this will skew the distribution towards larger values. So the least value will be fairly, and the difference between the least and the larger value will be fairly small. So that means you can afford to get greater distribution over the variation over the higher part of the key, so that you'll be left with more number of values for the in-between values for the lesser part of the keys, which will minimize the collisions. So this is one possibility. And you can also incorporate the dispersion. So you make use of one measure, which is a measure for central tendency, which is your mean, and you make use of another measure, which is your either your mean distribution, which is a measure of dispersion or spread, which is a mean deviation, or your standard deviation. So to define a reasonable hash function which will minimize collision.